First law of thermodynamics. This is module 4A, and in this module we're going to look at the conservation of energy, which is the first law, types of systems that we'll look at, and I'm going to show you ways to define your system that makes the problem easy to solve, and application to isolated and closed systems. So this is what we'll talk about in this module. First of all, we've got to cover the sign convention for heat and work. Now, I'm not in favor of having a sign convention personally, but when you pick up a book is going to stick to, often books will stick to a sign convention where heat is in, work is in, those sorts of things. So if we draw our system where we have heat coming in and work coming in, the book you're using has a sign convention. Qn is positive and work in is negative. The way I always do it is I'll draw my arrows according to whether I think the work is coming in or out. But when you're looking at answers that you'll have from the book, a negative number for a work would mean that it was actually coming into the system. I always use the boundary work out of the system. And so I'll draw if the system boundary is expanding, for instance. That means the fluid inside the system is pushing back the boundaries of the system. Then the fluid is obviously doing work to do that. Pushing back its boundaries requires work. So work out I consider to be positive, and so does your text. So work is the integral of P dV. So pressure times the volume. Recall we looked earlier at force through a distance. Force dot dx is work. So we showed that that's also P times dV. So P times dV of the system. If the system is getting larger, then the fluid inside has to be pushing back the system, and that means that the system itself is doing work to push back the system. So work out, the integral of P dV, we call that boundary work. Now let's look at the first law of thermodynamics and what it means. A lot of times the first law is referred to as the conservation law, meaning energy is conserved, meaning it's not created, it's not destroyed. It can be balanced. Since it's not created or destroyed, you can track it. You can find energy. If it changes from one form, it shows up as another form. So energy can be balanced like your checkbook. So we'll look at N, and this is I guess my favorite equation. N equals out plus what we call accumulated. So in your checkbook, if you put money in, $10 in, you take $5 out, then the net change is $5, or the change in the balance. We call these balances, and we'll be doing what we call energy balances. So we'll be looking at the change. I often call that accumulated. So N equals out plus accumulated. N equals out plus accumulated. Now in general, we can write a balance equation for things that are not conserved as N plus generated equals out plus consumed plus stored. So that's what we call a general balance equation. If you take a population balance on a state, say, the people that come into the state plus the people that are born in the state, generated, equal the people that leave the state plus the people that die, consumed, and the stored would be the number changing and the population change of the state. For energy, there's none generated and none consumed. Now energy can be generated from mass by remember the famous equation E equals mc squared. A nuclear reaction produces energy from consumption of mass. We're not going to look at that here. We're going to neglect those nuclear reactions and just look at N equals out plus stored, or N equals out plus accumulated. Stored, that change and balance of the system, let's say, that's the accumulated. That's the net change, and the net change can be positive or negative. If I had a gas, then I can see, remember, the energy of a gas is represented, or the stored energy of a gas is represented by its temperature. So if I have a gas as my system and the temperature goes up, I know I've Accumulated energy. I have a positive increase in energy, positive change in balance of the system. If the temperature of the gas goes down, then I have a negative or a drop in my stored energy of the system. So stored or accumulated can go up or down. Now we always do a balance on a system, and how you define your system can make the problem easy or the problem hard to solve often. And it's just a talent in finding or defining a system, and the way to get that talent is to work a lot of problems. Take a look at a lot of different problems, define your system, do the energy balance on the system, and you'll find that you get better at this, at defining your system. So it's often a system referred to as a control volume, so a part of space where energy goes in or out of the system will be what we call a control volume, or I'll call it often a system. You can also think of it as an account, where the balance of the account, the balance of energy in the account, goes up and down. And the system is whatever part of space you want to do your balance on. And again, there's a skill to developing this. So it could be the air in the room, or the whole room, including the air and the people and the furniture. Again, with practice you'll find that you get better at defining your system and making problems easier to solve by the way you define your system. Now we'll look at types of systems, and one of these is called the open system. In an open system, mass and energy can flow in and out of the system freely, and I think most real systems are open, but we can look at restriction to that. What we call a closed system, where energy can flow in and out, but mass doesn't flow in and out. I guess there are a lot of closed systems. If you look at a tank, closed tank, and you start to add energy to the tank, well, heat can flow into the tank and change the condition of the mass inside, but the mass doesn't come in or out of the tank. When we put a valve on the tank, then we can open the system and allow mass to flow in or out. And then we have what we call an isolated system. In an isolated system, neither energy or mass can flow in or out. So we have, let's take our tank. In the tank, heat could flow in or out, but now if we insulate the tank, then there's mass in there, but there's no way to get energy in or out because it's insulated and the heat can't flow in. If it's a rigid tank, then the volume of the tank won't change, so you can't have boundary work by changing the volume of the system, so you're not able to put work in or out either. So that would be an example of an isolated system. Now, I like to have a little table here. This is a little table that summarizes the energy changes that we're going to use in our energy balances. We can have a flow into or out of the system, and then we can have stored energy in the system. So for our flow in or out of the system, we have work, and there are different types of work. There's the boundary work. Remember, we talked about the system's boundary changing, the volume changing of the system, and that's the integral of PdV. And remember, that's work out if we specify it that way. Think about it. If dV is positive, then the system has expanded. The gas has to push back the boundary of the system. If dV is negative, then the gas, let's say, or the system is being compressed, pushed down, and so you had to do work from outside onto the system to compress the system. So the work in that case would be negative on the gas. We have shaft work, so you could have a shaft coming in or out of the system. You could have a spinning mixer that goes where work is being added into the system through a motor that spins a mixer inside the system, and that mixer will stir the gas or stir the liquid or the fluid inside the system. And by that stirring, you'll wind up adding energy to the system. Or you could have electrical work added to the system. Just put in a strip heating coil, and the electrical work from outside will go through the heating coil in the system and be converted to heat energy, which will add energy to your system. So that can flow in or out by what we call work. We have heat energy. Q is what we applied to heat energy, and heat can be added by making the environment of the system hotter than the system itself, and heat will flow downhill in temperature. Heat will flow into your system because the surroundings is hotter than the system. If mass flows, say we have an open system and mass can flow in or out, then mass can bring energy in, I guess, 4 ways. It can bring its internal energy, and that's due to the molecular motion of the molecules. Internal energy. If I bring the energy into the system, I had to do work to push the mass. If I bring mass into the system, I had to do work to push the mass into the system, and I call this flow work. P times V, remember pressure times the volume to push that mass in, is flow work. So we have U plus PV. And you recall that U plus PV is enthalpy, so often it's easier when mass is flowing in or out of a system just to use H instead of U plus PV. It covers both of those terms. The mass can also have kinetic energy, so if it comes in very fast into the system, it's bringing that kinetic energy with it. So that's adding energy to the system by the, let's call it the bulk motion of the fluid coming in or out of the system, or the solid fluid. Whatever it is coming into the system, if it's moving fast, then that, let's say, macroscopic energy is going to be added to the system. And again, potential energy. So if I have a system with a very large change in height in my system, if I come in at a very high elevation and go out at a very low elevation, then that mass can have a change in energy due to its potential energy when it comes in relative to when it leaves. Now let's look at the stored energy of the system. The stored energy can be delta U, change in internal energy, a change in internal energy, which again, if it were a gas, that would be reflected by a rise in temperature. You can have a change in internal energy because it changes phase while it's in the system. So if it goes from a liquid to a gas, from one state to another within the system, then the internal energy has changed for that reason. We also have a change in kinetic energy. If my system is an airplane and I start on the ground and I speed up the airplane and go to a higher velocity just before takeoff, then I've changed the kinetic energy of the system. Once the airplane takes off and starts rising up into the air, then its potential energy will also change. So depending on the system, it can have a change in kinetic energy, change in potential energy, and a change in internal energy. And we're going to use these terms to balance the energy of the system. We'll look for those changes in balance of energy, by looking at the interactions to the system. Flows of energy in or out of the system. Now, again, I mentioned earlier just now that U plus PV is replaced by enthalpy. And so we can say that H represents the internal energy plus the flow work to get the mass in or out of the system. So I like to think of H as the stored energy of a moving mass, where the mass is moving into or out of a system. Let's take a look at a closed system. Here's your house with a refrigerator in it. And the question is, let's say it's perfectly insulated. The house is perfectly insulated, and there's a refrigerator. Now this is a classic problem. The occupant leaves town and forgets to close the door. Now take a minute and ask yourself what happens. Go ahead and pause the video and ask yourself what happens to the temperature in the room. What happens? You've opened the door, and now there's this cold refrigerator facing the room. What happens? I come back from my vacation, and I have a perfectly insulated house, let's say. Not really realistic, but suppose it were. When I come back from vacation, what's the temperature of the room? Hotter or colder? What do you think? Well, we look at the system and we say in equals out plus stored. And the electrical work is coming in because we had that refrigerator plugged in. When we open the refrigerator, it's going to warm up a little bit, and the compressor in the refrigerator is going to kick on. It's going to start drawing electrical power from the plug outlet, and you're going to be putting energy in. Energy is going to come into the refrigerator, which ultimately is going to wind up in the room. So if our system includes the room, the refrigerator, everything inside, then the mass of the system times the change in internal energy of the system is balancing the electrical energy that we're putting in from the plug. Work coming in, delta U, delta T is greater than 0. So ultimately that's going to be reflected by an increase in temperature of the house and its contents. So if you open the fridge, immediately it'll start to cool down a little bit. But if you leave it long enough, the whole system will heat up. Let's look at another example of a closed system. Again, here we're talking primarily about closed system. So we have a piston cylinder arrangement where we have air inside the piston on one side. On the other side of the piston we have a vacuum. So we have 5 bars, so we have about 5 bars, about 5 atmospheres. That's pushing back on that piston. If I remove those stops, that's going to slam that piston to the right because I have that pressure and nothing balancing it, no pressure on the other side. I have a vacuum. So if I remove the stops, the piston is going to go to the right, and that air is going to push that piston back. It's an isolated system. It's insulated from the outside, so I don't have any room for heat transfer. If I take the system to be the chamber with the air and the chamber with the vacuum, then it's what we call an isolated system. Since it's insulated, Q is equal to 0, no heat transfer. By the way, we call that adiabatic. When Q is equal to 0, we call that adiabatic. If we calculate the moles in the system, remember PV over RT is equal to moles. We find we have 0.2 moles in that system. Let's suppose that's the moles in the system. Suppose that's a 1 liter on the left. There's nothing in the right hand chamber because it's a vacuum. We remove the stop and suddenly we have 2 liters. That piston flies to the right, 2 liters. Have you done any work? No, you haven't. The system includes, you haven't pushed back anything because there's no pressure to push back against. Now if we do our balance on the system, in equals out plus accumulator, you're going to do that balance over and over and over until you're expert at it. Delta mu, change in energy of the system. Remember, U is the specific internal energy, so the mass times the specific internal energy gives us the total internal energy. Delta mu equals, remember, delta U for an ideal gas is CV delta T. So in equals out plus accumulated. There's nothing going in, nothing going out, plus because it's isolated, so the accumulated term, which is delta mu, change in storage of energy of the system, is 0. So mCV dt equals 0, or dt, or delta T, is equal to 0 for this system. So the final temperature is the same as the initial temperature, 300 K. At the end of the process, P2 is now 2.5 bars. If we put in PV equals nRT and the volume has doubled, then the pressure, since the temperature remained the same, the pressure is cut in half. If you could plot this over what was happening with the gas as it expanded, then it would look something like this. You'd start up with a pressure of 5. This is an isotherm where the temperature is constant of P versus V for that gas. So at 5 we start out with 5 and a volume of 1. By the time the volume becomes 2, the pressure is dropped to 2.5. So all at constant T. Again, this is an isotherm. Now let's remove the isolation constraint, and let's allow the piston to push back against the atmosphere. So now our system is the gas in the system, and we're going to allow the gas in the system to expand. So we're not looking at the left-hand chamber and the right-hand chamber. We're just looking at the gas in the system. Treat that as our system. And we're going to slowly move these stops. Now, if we move these stops slowly, we're pushing back the atmosphere, so there's some work done as that piston pushes back the atmosphere. But the pressure in the system, the pressure of the gas, is higher than the atmospheric pressure. So what happens? The work done by the gas is PdV of the gas. The work received by the atmosphere is PdV of the atmosphere. Now the pressure in the gas is higher than the pressure of the atmosphere, so there's some work lost in the transition. The atmosphere doesn't receive as much work as the piston does. You have to think about that a little bit, but that's what's happening. Since the pressure is higher on the left, you would normally accelerate the piston. As soon as you left those stops off, that piston would accelerate and you'd have that kinetic energy formed. But here we're moving it slowly. So there's going to be some friction either in the gas or in the piston, and we're going to assume that all this friction energy goes into the gas, goes back into the gas. Again, the atmosphere is pushed back slowly, but the piston's not accelerated. We move it back a little more. Now as we move it back, it's doing work to push back the atmosphere, but that's a constant pressure. The pressure inside is dropping until finally it does meet the pressure of the atmosphere. If you let it go long enough, you'd finally push it back to the atmospheric pressure. But what we're showing with these little red arrows is that friction, as we slowly move it back, is going back into the gas and allowing the gas to heat up a little bit. If we look at our balance, N equals out plus accumulated, then N, again, what is N? N is 0, because we're not putting any work into the system. The work is going out. So N equals work out plus mCV delta T. Again, we're going to assume that this is adiabatic. Now, the work out is the work received by the atmosphere. The work actually taken out of the system is the work actually received by the atmosphere, which is the pressure of the atmosphere times the change in volume. That's 1 bar times approximately 1 bar. Let's assume the pressure of the atmosphere is about a bar. Standard atmospheric pressure is a little higher than that. But if we take our work out as 1 bar liter, because the change in volume was 2 liters, I'm sorry, 2 minus 1 liter. So that would be 0.1 kilojoules or 100 joules. Now I suggest you pause the video, convince yourself that that's correct, that those units are correct, because again, you want to get more and more proficient with units. We can then calculate our delta T, because remember, mCV delta T is delta U. So I'll take our work out, solve this equation above, or the energy balance that we had on the previous slide, and the work out divided by mCV delta T is equal to, the work out divided by mCV is equal to delta T. And we find that the temperature of that gas has dropped 24 degrees. Now in your common experience, you know that when you bleed gas out of a tank, the temperature is going to go down, because the gas is doing work against the atmosphere as it pushes out against the atmosphere. In this case, we had the gas still inside the piston, but its temperature drops because we've had to push back the atmosphere and take out work. So T2 equals 300 minus 24, or 276 K, and we can calculate from the ideal gas equation our new pressure, 2.29 bars. The work done by the gas is more than the work received by the surroundings, but that work wound up as friction and went back into the gas and wound up heating up the gas a little bit. Had we let that gas expand, against a higher pressure load than the atmosphere, then it would have done more work and the temperature would have dropped, more actual work, and the temperature would have dropped further. The difference, again, is dissipated. The difference between the work that the gas did and the work received by the surroundings is dissipated and winds up as friction. The gas that dissipated from friction with the walls of the piston, or friction just by the gas swirling around inside against itself and causing friction, which winds up increasing the temperature. The temperature would have dropped further had there been a larger load against the piston. Let's get rid of the friction now and use that load to balance the internal pressure. Assume that the load is actually balanced the internal pressure. So we move the divider such that P internal equals P external. Now to do that, we have to have a completely frictionless piston. We have to oil that piston so that there's no friction against the sidewalls, and we have to move it slowly enough so that the gas doesn't swirl around on itself. And in that case, the P internal equals the P external, and we'll see what happens. The work done by the gas equals the work received by the surroundings. Now that's a perfect machine. Do our energy balance, and we'll do it on a differential level, so P dV equals mCV dt. Plugging in the pressure as a function of T, because we can't integrate P dV unless we have P as a function of T, we solve for P MRU T over V molecular weight. Follow those equations. Again, I encourage you to pause the video, work through these equations, convince yourself that all this is true. Mathematically it is. And you'll see that RU over molecular weight dV over V equals CV dt over T. Now you look at each side of that equation, you say, hey, that's something I can integrate. dV over V, that's ln of V. dt over T, that's ln of T. We perform the integration, rearrange, do a little algebra, and we find that the temperature in this case, where more work is done against the surroundings, more work is exported to the surroundings, and the temperature of the gas has to drop further because it's doing more work and its energy drops further, all the way down to 227 K. So for homework, what I'd like you to do is find the work done actually by the gas and find the final pressure of that gas. That's one homework assignment for you. Again, we reviewed in this module, we looked at types of systems. We looked at isolated, where there's no movement of mass or energy across the boundary. We looked at closed systems where there's no movement of mass. And we haven't looked at, but we defined what an open system is. Mass and energy can move in or out of the systems. And we'll get to that later in a later module. Applications for this, we looked at the use of the energy balance. We looked at process interactions such as work. And remember, work out is the integral of P dV. And we used property relationships that we've learned before, such as PV equals nRT and du equals CV dt. So those are how we've applied some of the knowledge we know to solve problems. Here we looked at this whole module was all about the conservation of energy, which is the first law of thermodynamics. N equals out plus accumulated. You can use that equation over and over and over again until you just, like I say, I'd like you to be expert at it. Just work, I don't know, 10,000 problems and you'll be getting there. For homework, start doing this. Read chapter 4 and work as many of those energy balances as you can to be proficient with this material. I'd suggest you start by working, say, problems 1 through 100, particularly the ones that have answers. Those problems in your book up through about, I guess 96 is where a good place to stop. Look at the problems that have answers first. And again, I'll post some more problems for you to get proficient at this. The more problems to do, the better you're going to be at this. So get out there and just start working problems now.